Hi, everyone. My name is Jianan Li from University of Pittsburgh and Pittsburgh Quantum Institute. Shivendra cannot come to this talk, so I will give this presentation on his behalf. My talk today is about our graphene lithium aluminate and strontium titanate nanostructure. So we know that the 2D or semi-2D material has been attracting a lot of attention because their unique physical properties compared to their 3D counterparts. So this is an incomplete list of 2D system or 2D structures, and yeah, this list is actually still growing over years. And this talk will be focusing on the lithium aluminate and strontium titanate heterostructure and its combination with graphene. Lithium aluminate and strontium titanate are two kinds of perovskite structure oxide materials. The extraordinary thing about this heterostructure is that once the top lithium aluminate is more than 4 unit cells, there will be a layer of 2D electron gas formed on the interface. So when the LaO is between 3 and 4 unit cells, the interface is insulating, but we can make it conductive by sketching a FM tip with a positive voltage. So the interface will become a canvas for creating nanostructure on demand. So successful stories include this sketch single electron transistor, or creating this fiber probe cavity, or writing this quantum point contact device. And this actually helps us understanding properties of the material itself as well. And recent discovery include this electron pairing without superconductivity, and this is actually in an invited talk on Friday morning. So this is a demonstration of how we can create a nanostructure on the interface. So the tip apply a positive voltage and create this channel of nanowire. And also we can erase this nanowire partially by applying a negative voltage. So the question is, can we create can we combine the versatility of the graphene with the writability of our SrTiO system and create a graphene LaO₃ nanostructure on demand? So first thing we tried was using this conventional PMMA transfer technique, and actually we found that after the transfer process, there's a lot of residues on the surface of LaO, and actually the sample is not writable anymore. I think our writing actually follows this water cycle mechanism. That's the tip will detach the proton from the water molecules absorbed on the surface, and the proton actually drag the electron onto the interface of LaO₃, so that's actually creating the 2 electron gas over the written area. So somehow the remainder of PMMA was preventing us from doing this and make the sample not able to be written anymore. And we actually found this replacement of PMMA, that's HiFLON and FC40. So HiFLON is a kind of a perfluorinate plastic, and it's chemically inert, and it's only solvable in FC40 but not in water or acetone or IPA. So FC40 it's another kind of fluorinate solvent. So we put HiFLON into the FC40 and spin coat that onto the CVD grown graphene on copper. And after the transfer, we do this normal photolithography process. And because the HiFLON it's not solvable in acetone, so it's actually totally intact over the process until the last step. We dissolve that with FC40 and get a clean LaO₃ graphene sample. And this is a pattern sample. So we see that the graphene is relatively clean, and there were some particles left on the surface, but those can be easily removed by the contact mode scanning with FM. And we see that in this picture, yeah, lattice the terraces of the LaO is pretty visible, so we know that the sample is atomically clean. So the most important thing is that the sample is still writable after this transfer and patterning process. The way we prove that is using this piezoelectric force microscopy. So after we create this nanowire between two interface electrodes, we apply an AC voltage onto that, and we can modulate the carrier density over the channel. So this change of carrier density will modulate the topology of the surface as well. So in this way, we can see this those written areas are actually visible on the PFM image. So we create this nanostructure with part of the nanowire underneath the graphene to see if we can write underneath that. So we actually see that it's a pretty clean PFM image of the nanowire, both outside the graphene and inside the graphene. And the connectivity of the nanowire is about 100 or 200 nanosiemens. And this is another structure we created. So, so part of the nanowire is actually underneath the graphene area, and we use the graphene as a top gate. So we see this clear tuning effect of the graphene top gating, and there's minimum hysteresis, so we know that the wire can be successfully tuned by the graphene. And this has been published last year. So also we did some transport measurement on the graphene as well to see the quality of it. And it turned out the graphene is pretty high quality, and the mobility is about 10 to 30,000 into Kelvin. And the carrier density can be well tuned by the backgate voltage as well. So, and also we see this clear LaAlO levels even up to nu is equals to 100 in the RxY channel. Well, another interesting thing we saw is this weak anti-localization in low temperature and even up to room temperature. So I think this is the first time we can see the quantum transport even persistent up to room temperature. So this has been posted on the archives already. So in summary, we can create nanostructures on the LaOH interface, and PMMA was replaced by the high flown, so the sample is still writable after the transfer and patterning of graphene. And the nanowire written underneath the graphene can be imaged with a PFM, as we show, and the graphene is still pretty high quality even after the patterning and the writing process. And we see the signature of room temperature quantum transport in graphene, lanthanum aluminate, and strontium titanate heterostructure. So that's all I want to say, and if you want to know more about the LaOH system, we have more talks in the future, in the following days, and thank you for your attention.